Hello. Now, we had discussed about the Sommerfeld theory as well as the Bohr's model prior to that. And in both the cases, there were shortcomings. In fact, in the Bohr's model, which was a classical atomic model in which quantization was introduced arbitrarily, failed to give a complete explanation of the behavior of the atomic systems. And therefore, classical mechanics must be replaced by a theory of greater generality, and that's where quantum mechanics comes up. And it was developed by Schrödinger, and the equation that followed was helpful in interpreting the various aspects of at the atomic level. So to start with the Schrodinger equation that we come up, we first introduced the wave function psi, which was capable of describing a system in its entirety. So first up, we have the Schrodinger equation. This one that I'll be writing is time independent. We also have the time dependent Schrodinger equation. But first up, let me write the time independent one. So this is del squared psi being the wave function which is used to describe the system, the wave function which describes the entire system or gives information about the system, and because it is associated with the system. So del squared psi 8 pi squared m over h square E minus the potential energy term, that is the total energy minus the potential energy, times of psi is equal to 0, and this is the Schrodinger time independent or steady state wave equation for a particle. It can give all the information about the particle that is required. Now, the we must know the physical interpretation of the Schrodinger of the wave function. It was given by Born in 1926, Max Born, and he suggested that, as per his interpretation, the probability of finding the particle within an element, let us say an elementary volume, d tau, in that volume the probability is given by psi squared d tau, and that when integrated over the entire space must be unity because the particle is obviously present somewhere. So, and that space that we are talking about, maybe in this case we are considering the atom as a whole. So in that case the probability of finding the particle, let's say electron, that has to be 1. So the wave function that obeys this equation is said to be normalized, and every acceptable wave function must be normalizable. Now it is also required that the wave function, first of all, it has to be finite everywhere. If suppose psi was infinite for a particular point, the same would be true for the wave function, uh, uh, let us say in the probability the probability of finding that particle at that point, that would be infinite as well, and this would violate the uncertainty principle. So as you know, the uncertainty principle tells us that you cannot determine the position and the momentum simultaneously for a microscopic particle. So therefore psi must be finite, or maybe 0 uh, at any given point. Secondly, it must be single valued. If it has more than one value at a point, it would mean that more than one value of probability of finding the particle at that point, and that is obviously ridiculous. And in the third case, it must be continuous, continuous and have a continuous first order derivative everywhere. This is necessary for the Schrodinger equation itself because you have the second order derivative which must be finite everywhere. So this can only be possible if the first order derivative has no discontinuity at any boundary where the potential changes. So furthermore, the existence of the first order derivative as a continuous function implies that psi 2 is continuous across a boundary. Now, these requirements, which must be fulfilled by an acceptable eigenfunction, carry great significance. When this Schrodinger equation, steady state equation for a given system, is solved to obtain an eigenfunction which fulfills these requirements, then we find that the equation can be solved only for certain values of energy of the system. And thus, energy quantization appears in quantum mechanics as a natural feature of the solution to the wave equation. And the values of energy for which the Schrodinger equation can be solved are called as the eigenvalues. Now we shall shift our focus to the one electron atom. Now the one electron atom, just like the hydrogen atom, it is the simplest bound system that occurs in nature. It consists of a positively charged nucleus and negatively charged electron moving under the Coulomb attraction and bound together by that attraction. The nuclear charge is Z times of E that we know of, Z here being equal to 1. Z is equal to 2 for singly ionized helium atom. Nevertheless, singly ionized means it is a one electron atom. Now, the three-dimensional character of the system allows it to have angular momentum as well. In one electron atom, the electron of mass, let us say small m, it moves about the nucleus of mass, let's take it as capital M. And they move about a fixed center of mass. And we may replace this actual atom by an equivalent model of atom in which the nucleus is infinitely massive and the electron has a reduced mass mu. So we have a reduced mass from both these masses. That means we have m times of m over m plus m. So this is the reduced mass of the electron. Now, the reduced mass electron that moves about the infinitely massive and therefore it will be stationary, that is the nucleus. We are considering this, that the nucleus now is treated as infinitely heavy and it is stationary, and the electron is moving about the nucleus with the same separation, that is the same electron nucleus separation as that in the actual atom. Now, the potential electron with the reduced mass, it has a Coulomb's potential, and the potential is given as a V is equal to, it depends on all the three coordinates, that is x, y and z in the three-dimensional space. So this is negative of ze squared over 4 pi epsilon naught times of the combination of this, the resultant position vector, which is the under root of the sum of the individual coordinates. Now this is obviously, let me tell you, this is obviously r as we know it. This is x squared plus y squared plus z squared, all under root. They are the coordinates. Now the Schrodinger equation for such a system has been provided as earlier. Instead of that m that we see at the top, it is now replaced by the reduced mass. So in this case we have this as 8 pi squared mu over h square E minus u times of psi, that is equal to 0. And this let me correct this. This is the potential energy term. So although it is written as potential, it's just potential energy to make sure we are just not confusing with the notations over here. So we'll take it as u instead of the general v. And since we are considering the Cartesian coordinate system, so we must know that this del square is simply the expansion of that del square will give us this. So that del square, that is the Laplacian operator that we see at the top, that is the inverted triangle. The expansion of that is simply the second order partial derivative with respect to all the individual coordinates in the three-dimensional space. Now this equation that we have over here, that can be broken into three simpler equations. A single equation, it's better to solve three different equations with one variable coordinate. Well, that is possible if we are just using those coordinates, that is x, y, z, instead of that del square, then we can do that. But the problem lies with the potential term, because that depends on x, y, and z as well. And that's difficult to separate in the, not possible. So that being a function of all the three coordinates. So the difficulty is, however, reduced by considering the spherical polar coordinates. This entire thing that we have, that is the x, y, z coordinates, they can be simply be taken as r, to be dependent on r, and we can keep the potential instead of taking it as an expansion. There is no expansion for potential in the x, y, and z coordinates, because it is a combination of all of them. So it's easier if we replace the coordinates x, y, z by the spherical coordinates, spherical polar coordinates, that is r, theta, and phi, which makes things really easier. You will see how. Now from this figure, if you can see that we have chosen the coordinates, the axis x, y, and z, and the particle which is lying at the point P now, it has the coordinates x, y, z, but that when represented by the spherical polar coordinates, that can be given as follows. If we look at it, x will be equal to r sine theta times of cosine phi, and then we have y is equal to r sine theta times of sine phi, and finally we have a z which is equal to r cosine theta. Now the radius vector, as we know, is simply x squared plus y squared plus z squared, which is easily satisfied by the above relation. So this is taken care of, and the polar angle, that is theta, here will be cosine inverse of a z over r, from this relation that we have over here, z over r, and r, as you know, is a combination of these three Cartesian coordinates. And the azimuthal angle, that is, this is the polar, this is the azimuth, the azimuthal angle phi is equal to tan inverse of y over x. So these are the relations, and using these relations in the Schrodinger equation in the spherical polar form can be given as follows, that is 1 over r squared del over del r, r squared del psi over del r, plus 1 over r squared sine theta del over del theta sine theta del psi over del theta, plus, it's not over yet, plus 1 over r squared sine squared theta del square psi over del phi squared, plus 8 pi squared mu, this is the energy term, over h squared E minus u times of psi is equal to 0. So that's the Schrodinger equation in the spherical polar form. We'll see how it's easy, because the potential, as you know, the potential is still the same. We had it as u depending on r. So u is equal to u of r, which is equal to minus z e squared over 4 pi epsilon naught r. So it stays as such. So it is the simplification that was provided. It may look complex right now, but when you look at the separation of variables, when they are taken into consideration, you will find that this is really effective, this process that we just carried out. Now the separation of variables, as for that, now we have psi, which can be represented as r, theta and phi, and as for the separation of variables, first up we take it to be dependent on one of the variables is taken to be dependent on r, while the other one is dependent on theta and phi. So one is the radial function and the other one is the angular function. Now if we use this in the Schrodinger equation that we have, then what do we end up with? Well, we end up with something like this, which is 1 over r squared d over dr. Now we can write the proper derivative because we have now separated those variables, dr over dr y, plus 1 over r squared sine theta d over d theta sine theta dy over d theta times of r, plus a lot more terms, 1 over r squared sine squared theta d square y over d theta squared times of r, plus 8 pi squared mu over h squared, and that is multiplied to E minus u times of r y, which is equal to 0. So this is now the Schrodinger equation with the variables that we had chosen depending on different coordinates in the spherical polar coordinate system. Now if you take a look at that equation, you may write it somewhere for your benefit. Now if we divide that entire equation by a factor r square over ry, then, and we rearrange them, then what do we get? We have the 0 on the right hand side, so what we get is we separate the r terms remember u is dependent on r, and on the other side we have the angle dependent terms, which is something like this. So the left side of the equation is completely dependent on r, while the right side is dependent on theta and phi. This equation can be correct if both the sides of the equation are equal to the same constant. We choose the constant as L times of L plus 1. So we introduce another variable. So from that, what we get is, let's say they are equal to, we'll take it as L times of L plus 1. So both these equations, this side as well as this side, they must be equal to this common term. So we have 1 over r, d over dr, r squared dr over dr, plus 8 pi squared mu, and there was the r square. We can take the r square, multiplying that r square over there. So e minus ur, that is equal to L times of L plus 1. And also we have minus 1 over I, the entire bracketed term. I'll have to rewrite it for you and for myself as well. This is complete derivative. This last equation that we have over here, that has two variables again. Y is dependent on theta and phi. Well, let's choose something else which will be depending on them individually. So we introduce another function which is, let us say, this kind of theta, the capital theta, which is depending on theta, and we introduce the capital phi, which is depending on phi. So the bigger theta and the bigger phi are depending on those smaller variables, and this would give 1 over theta phi. You can come up with any other symbol which is much easier to write, if you may. And then we have 1 over sine theta d over d theta. Now the theta and the phi terms will get separated, so probably we could have used the partial derivative over here instead of the proper derivative, because that would help in separating those variables. So we'll keep them as partial derivatives instead of the proper derivatives in case of y, because we still have to separate two more terms. So I've changed all of that. You can change it yourself as well. Sine theta d theta, that is the capital theta, over d theta times of phi, plus 1 over sine squared theta d2 phi over d phi squared times of theta. All of that is equal to L times of L plus 1. Now this again, by dividing or multiplying, actually here will be multiplying. So by multiplying sine squared theta and rearranging, what we get is, we now separate these variables as well. So we have 1 over the big theta sine theta d over d theta times of sine theta, again del theta over del. This can be complete derivative over here because there's no problem with that. Plus we had the L times of L plus 1, which is depending now because we have multiplied sine squared theta, so it's now depending on theta as well. And on the right hand side we take 1 over phi d2 phi over d phi squared. Now obviously we multiplied the sine theta because to get rid of the sine square theta over there, so that becomes completely taken care of. Now with this, these two will be now equal, both the sides, if they are equal to something else, just like we had the case over here that both of them were equal to L times of L plus 1. We'll take this as to be equal to something called as ml square. We'll be giving names to those variables that we have taken later. Some of you might be knowing, in fact most of you might be knowing that, but we'll keep it as a suspense for now. We know this, it's a known suspense. Now with this constant and both those sides of the equations being equated to that constant, what we get is we get 1 over theta. So that part of the equation is there. Now these all these equations, if we write them directly, so this is d2 phi over d phi squared, and there was a phi over here which goes cross multiplies to that ml square over there, which comes to this side and becomes positive, or this can be taken to the other side and that becomes positive. Choose it any way you like, and that is equal to 0. So this is one of the equations. The other equations will be, in case of this being equated to ml square, what we get is 1 over sine theta d over d theta sine theta d capital theta over d theta plus L times of L plus 1, we'll keep it in square brackets, minus ml squared over sine squared theta multiplied to the bigger theta is equal to 0. So this is one equation, this is the other equation, and the third equation, as you know, is written over here somewhere there. It was this one, I guess. Yes, we can rearrange that, we can write that properly. Rearranging, we'll get 1 over r squared d over dr, r squared dr over dr, plus this one will be a bit of a big term, 8 pi square mu over h squared. The r square that was multiplied over there has been taken the other way around, so e minus ur minus L times of L plus 1 over r squared whole multiplied to capital R, and that is equal to 0. So we have these three important equations with the variables separated. Now the solution to all of those three equations, first of all we have to introduce the quantum numbers, which were already introduced, of course, but now we know that they are just quantum numbers that had been introduced. So let's consider the first case where we are considering the solution for phi ml, which depends on phi, has the solution a e raised to the power I ml phi. is a constant of integration, and this solution, in order that it is an acceptable solution, the wave function that is provided over here, that must be single valued function of the position, that is, it must have single value at a given point in space. And it is evident that for the azimuthal angles, phi and phi plus 2 pi are actually the same angle in a given three-dimensional space. So it must be true that we have phi ml of phi to be equal to phi ml of phi plus 2 pi. And as a result of that, we must also have a e raised to the power I ml times of phi is equal to a e raised to the power I ml times of phi plus 2 pi. And that gives us 1 on this side to be equal to e raised to the power I ml times of 2 pi, with the terms cancelling out. And as a result of that, we have I, that is 1, to be equal to cosine ml 2 pi plus I times of sine ml 2 pi. And this can only happen if ml is either 0 or positive or negative integer, and that is ml will be equal to 0, plus minus of 1, plus minus of 2, and so on. So the constant ml is a quantum number of the atom. Now let's look at the second case. Now in the second case, in the second equation for theta, which is dependent on theta, the solution will be theta LML. That will be equal to N LML PL and the modulus of ML cosine theta. P here is the associated Legendre polynomial. Associated Legendre polynomial. Obviously, it will have different forms for different values of L and ML. This solution is acceptable only if L is an integer equal to or greater than ML. So we have L to be equal to ML, ML plus 1, ML plus 2, and so on. This requirement can be expressed as a condition for ML. That means ML can be 0, plus minus 1, plus minus 2, and it will continue not till eternity, but it will continue to the maximum value being plus minus of L. And the constant L therefore is another quantum number. Now the third case, as for the radial condition, we have RNL, which depends on R, to be equal to N NL e raised to the power minus Z times of R N times of A naught 2ZR over NA naught raised to the power L. Then we have a polynomial just like the Legendre polynomial. This is the Laguerre polynomial, 2ZR over NA naught. So as I said, this is the associated Laguerre or Laguerre polynomial. And it has also different values for different values of N and L. The parameter that we have introduced, A naught, is simply equal to the constant value, that is h squared epsilon naught pi mu e squared, e being the charge of the electron. And this is, as per the old quantum theory, the smallest Bohr orbit of hydrogen atom. Now the above solution is acceptable only if the constant, that is E, is positive or has one of the negative values En, which corresponds to the bound state, which is given by that we had obtained in the Bohr's model. Now for that, N will be equal to L plus 1, L plus 2, L plus 3, and so on. So it must be equal to or greater than L plus 1. This requirement may be expressed as the condition that L is equal to 1, 2, 0, and then it continues up to n minus 1. So there is a restriction in the value of L, there is a restriction in the value of ml, and n obviously is also another quantum number which we have just introduced. Now the total eigenfunctions of one electron atom that can be written as follows, that we have psi, which is psi l n ml or n l ml, to be dependent on r theta phi, to be equal to r nl, which is dependent on r theta l ml, which is dependent on theta, and phi is the product of all of these three functions. Now the constants that are they are so adjusted so that each is normalized, and the real form of the normalized eigenfunction for the ground state, which is n is equal to 1 for the ground state, which is n is equal to 1. L can have n minus 1 value, that is L is equal to 0, and so is ml, which is restricted up to the value of L. So we have the eigenfunction for the normalized eigenfunction for the one electron atom. We put in these values, and we have the expression for r theta and phi. We have psi 100 nl ml, that is equal to 1 over root pi times of z over a naught raised to the power 3 over 2 e raised to the power minus zr over a naught. This is the expression this is the real form of the normalized eigenfunction for the ground state of a one electron atom. And we shall continue about the interpretation of the quantum numbers, as well as the electron probability density, and many more to come, but that will be in the upcoming videos. Till then, thank you for watching.